In this video we're going to look at a magnetic fields question. Pause the video now and try all parts of this question. Part A, explain how the magnetic field maintains the ion in a circular orbit. This comes up all the time. So what are the key elements of an answer? The force from the magnetic field, or due to the magnetic field, is at right angles to the motion of the particle. So that's the condition for circular motion. So you could then say this magnetic force provides the centripetal force. Or you could say this is the condition for circular motion, that force is at right angles to the motion. Part B is a classic. This comes up all the time. Derivation of an equation, usually similar to this form. So what do you need to start with? You need to start with the fact that the force due to the magnetic field is given by BQV. You also need to say that this is equal to the centripetal force mv squared over r. So now if you rearrange that, you end up with mass is BQVR over V squared, and obviously the V's cancel, BQR over V. That's not quite the answer that we want because we've still got this R and the V. So what's the next stage? Well, we need to say that the velocity is obviously equal to distance over time. It's moving in a circle, so what's the distance? It's 2 pi r over the time period. Now we don't want time period, we want frequency, but we know that frequency is 1 over time period, so 2 pi rf, and that is equal to v. So now we can say that r over v is 1 over 2 pi f. I've chosen to put it into this form because that is exactly what we've got here. So now substituting in, we get mass is BQ divided by 2 pi f, which is what has been asked for. Part C, explain how the electric field prevents the ion moving vertically. So we've got the ion here, and we've got the electric field is given by these two positive and negative plates, and you can see what they end up doing. They end up creating this field here in this shape. So why won't it move vertically? If it goes up, it will be repelled. If it moves down, it will be repelled. So there are positive, or there is a positive field above and below the ion, repelling it if it moves up or down. Part II. The device is known as a penning trap. It can be used to determine the mass to this accuracy. Confirm that the mass of a sulfur ion can be measured to the nearest 0.00001 U, where U is of course the atomic mass unit, which is the mass of one nucleon. So how can we get it to 3 in 10 million? So what we need to do is work out what 3 in 10 million parts of this are. So 1/10 millionth of a part is obviously 10 to the 6, but we want 3 10 millionths of that. So let's see what that equals. 32.0645 times by 3 divided by 10 to the 6. So this gives us 9.6 times 10 to the minus 5. What did we have here? We had 1 times 10 to the 1, 2, 3, 4, 5. So 1, 2, 3, 4. Yeah, that's fine. Is greater than 1 times 10 to the minus 5. So it's actually far easier if you write it out, I think, in normal numbers. So if you write it out as normal numbers, 0.1234 1, 0.11996. So if you write it out like this, you see that obviously this is clearly bigger than this. But for some reason I was struggling with this. But it's clearly bigger than our smallest measurement, which means it's fine to measure. Part I. Calculate the loss in mass of a sulfur ion when there is a gamma ray with a known energy of this. So what we need to do is work out what this corresponds to in mass. So 2.2 MeV, we're going to convert into mass. So our first step is to convert it into joules. So 2.2 times 10 to the 6, that will get it into electron volts, times by our conversion factor to get it into joules. Gives us 3.52 times 10 to the minus 13 joules. We're now going to go joules to kilograms. We're going to use E equals mc squared. So 3.52 times 10 to the minus 13 divided by 3 times 10 to the 8 all squared. Which gives us 3.91 times 10 to the minus 30 kilograms. And then we need to go kilograms to atomic mass units. So we need to do 3.91 times 10 to the minus 30 divided by our atomic mass unit, which you can obviously look up on the formula sheet, 1.66 times 10 to the minus 27. Which is 0.002 atomic mass units, so that should be a U, not a mu. And clearly this is bigger than our smallest measurement. So 0.002 is greater than 0.0001, which means it can be measured.